Today we are going to discuss assumptions related to strength of materials. That is, in structural analysis for strength calculations. So we need to have some assumptions. As you all know, basic sciences, any science if you see, so it must be, we must have some assumptions such that we will be analyzing or we will be understanding the things clearly, or we will make our analysis simple rather complex. So these assumptions, what are the assumptions on which the strength of material, the subject, our subject, which is related to gate or wherever. I cannot limit it to gate. So basic strength of materials is based on these assumptions. The assumptions we will discuss one by one. The first assumption would be the material of a body has a solid and continuous structure. So what do you mean by that? So we need to know. So there are different types of we know the mechanics is divided into various we have different mechanics like for example quantum mechanics, continuum mechanics. So this particular subject is based on continuum mechanics. So that is it is obvious that solid and continuous structure we need to consider, that is without any, suppose if you are considering a bar here or any element material, so we don't consider any voids if you have suppose some sort of cracks. Okay, so this should not be there. So material is assumed to be continuous and solid. So this first point is, I mean the basic assumption is this one. So you can understand while we study this Saint Venant's principle, we can correlate with this thing again. Then coming to the second point, that is within the limits of the part of the body. So we basic thing is, I want to say the material should be homogeneous and isotropic. So what do you mean by this homogeneous and isotropic? What do you mean by homogeneous and isotropic? So individually if you see basic definition, if you see, but the antonym for this homogeneous is heterogeneous and isotropic is anisotropic. So there will be materials which are anisotropic, heterogeneous also. So coming to this homogeneous, if suppose I may assume any body like this, if in a body or in a particular element of a body at every point in a particular direction, if the properties are in a particular direction, I am taking, if the properties are same, suppose we are interested in stress calculations in this particular subject, we will talk about stress here. The stress is same in all directions. Okay, this is about homogeneous material. What about this isotropic material then? Suppose consider the same element is another an element of any other body. If you consider at a particular point, at a given point in all directions the properties are same. Suppose whatever may be the direction I take here, whatever may be the direction I take at a particular point, the properties are same. Again, if you consider sigma here, I mean stress. Okay, so the elements which we consider for analysis in strength of material should possess these two properties. So if you draw it, a material should have both of these properties. That is at any given point or at all the points in all the directions, the properties are same. The properties are same. So everywhere the property is same, that is sigma. So this makes our analysis simple. If you make this assumption, everywhere it is sigma. Okay, every point throughout the material. So this is homogeneous and isotropic. So try to understand, so try to check what are the definitions of anisotropic. So based on this, we can say, suppose at every point in all the directions properties are same, what could be anisotropic, which is also called allotropic? The properties will not be same. It in the means anisotropic in the sense, if you consider this one at a given point in all the directions, the property is not same. The properties are different. Okay. So there is another term. So apart from this anisotropic, there is another term called orthotropic. So what do you mean by orthotropic? So orthotropic is also a type of anisotropic, but at a given three mutually perpendicular directions, the properties are different. What could be the example for this? So this falls under this example, that is wood. If you consider wood, if you consider, try to understand, try to check the texture of that wood, try to search for the images, so you understand. So what exactly is this anisotropic or orthotropic? So what could be the examples for other examples for this homogeneous and isotropic material? Suppose homogeneous material is whatever the base metals, if you consider base material, suppose aluminium, basic elements of whatever may be the available materials we have, so all can be considered as homogeneous. And isotropic materials, if you take the example, any powdered, fine powdered material of any material which almost we can neglect the any micro cracks or any voids in that. Okay, we cannot assume them actually. So that fine particles can be considered as isotropic. And one more thing, homogeneous material, wood is one element which wood is one material which can be considered as homogeneous also. Why? Because what is the definition of homogeneous? In a given direction at a point, the property is same. In a given direction in all the points. So in three directions, if you see in the wood, suppose if you take the direction along the grains in a tree, okay, the properties will be same at any point in that particular direction. So wood can be considered as homogeneous also. So this should be the attribution for the materials. This is the second assumption we will make to make our analysis simple. So further, our next assumption is self-weight is ignored. It is simply put here, but what do you mean by self-weight is ignored? What do you mean by that? So we have to consider that initially before loading, in order to analyze what could be the deformation or what could be the internal forces generated because of that particular external load, we have to initially assume that there is no internal forces. That is, its self-weight is ignored. So, so what if even there are conditions we will study in our future videos, that if self weight is considered, what could be the condition? So this lead to, if self weight is considered, this lead to analysis of a bar of uniform strength. A bar of uniform strength. How it looks like? Basically a bar of uniform strength. So when a bar is subjected to a particular load, it has got certain deformation. Okay, and without load also, due to its self weight, there may be. So if I draw curve related to its load distribution. Okay, so how the load is distributed in this? The load distribution could be this way, rectangular load for externally applied load. So if you consider the self weight also, what could be the load here? The load where is like this. So at this particular end, there will not be the material will not be available. Okay, so the load distribution will be like this. So if we consider self weight, the load distribution is like this. So the distributions together, if we consider self weight also, there will not be any uniform load distributed here. So which leads to analysis of some non-uniform stresses will be induced in this. So to make that stress distribution uniform, so we will consider, rather than instead of providing this prismatic bar, we will consider a bar of uniform strength which looks like this, somewhat like this, of a bar of uniform strength. So we will be analyzing this part also while discussing this basic stress and strain. Okay, so this is the modification you might have observed in some structures outside somewhere. So instead of this prismatic bar, so we will be providing bars of uniform strength. So that is when this particular assumption is failing. I mean, if you want to overcome this assumption, then our next assumption is principle of superposition is valid. So principle of superposition, what do you mean by principle of superposition? So let me give you that, so what do you mean by superposition here? So let us take a beam which is loaded like this. Whatever may be the beam, I supposing here cantilever beam, so which is loaded. Suppose at the free end it has got a point load, and so from the fixed end till some length a distributed load, that is uniformly distributed load, is applied on a beam. So how could you solve this? Okay, so in particular if I want to speak, so let us take the direct case. So this particular assumption is useful in solving proper cantilever beam. If I provide a support at the free end in a cantilever beam, it is called as a proper cantilever beam. That this particular assumption is useful for that in solving this kind of beam, and this kind of beams are called as statically indeterminate beams. So in this what happens, how do you solve this? Basically this problem can be solved, or this can be put, this beam can be put in such a way that we can solve it separately. That is a beam with UDL, also a beam with point load. So whatever the deflection you achieve from this and deflection you achieve from this, club it together. Suppose the deflection from this you get is delta 1, and deflection from this you get it as delta 2. So whatever the deflection here you get, so this will be equal to the sum of these two. So in solving such kind of loading, so we will be using this particular assumption. Then, so where it is actually superposition of, I mean principle of superposition is valid. So it is valid for linearly elastic members. So only the members which are subjected to the loading up to its elastic limit. Up to that point we will be using this particular principle of superposition. And where it is not valid, so in some cases where where the external loads tend to change the geometry of that particular member, this is not valid. That is, principle of superposition is not valid in some cases like this. That is long columns. So what happens in long columns? Long columns tend to buckle. Okay, so if you observe, so if I draw a long column like this, so which type of long column it is? This arrangement is hinged or pinned long column. So it tend to buckle. So upon application of load, it tend to buckle. That is, lateral displacement will be there. So this lateral displacement, because of its geometry change, so it is not pertain to this particular assumption. Okay. Next, non-circular member subject to torsion. So as we see in the overview of syllabus, one point I mentioned that torsion of or if you consider the syllabus of GATE, it is given only the we will be studying only the torsion of circular shaft, and the circular shaft is subjected to some assumption, that is Euler-Bernoulli assumptions, and these assumptions are pertain to circular shaft, I say. So we will be suppose if we have a rectangular or square cross section. Okay, this principle is not valid for that particular cross sections. So it is valid for only circular cross sections when subjected to torsion. Because of that non-circular cross section, Euler-Bernoulli assumptions may not be applicable for that. Thereby, the torsion concept will not be applicable for that. So we need to we cannot apply this particular assumption. Okay. Next, deep beams. So where do you use these deep beams? Concrete structures, deep beams are used where it tend to change its geometry, or it needs additional supports. So it cannot be analyzed as we analyze the other beams in our particular topic called shear force and bending moment topic. The beams we study is not similar to this deep beams, so it requires another kind of study. So that is why this assumption is not valid for deep beams. Then members with sinking supports. So what do you mean by that? Some supports, if just try to understand, suppose a member, I consider a fixed beam like this. Suppose this fixed support, one of the fixed supports is tending to sink. So what happens? That fixed support will tend to stress this beam, or tend to change the geometry of this beam. So what happens? This beam tend to change its shape, geometry. So upon changing this geometry, obviously based on this assumption itself makes that it is not valid. This assumption is not valid for this because its geometry is changing. Okay, so this is this particular assumption where principle of superposition, wherever it is applicable or not applicable, we have studied here. Next, coming to the Saint-Venant's principle. So Saint-Venant's principle is valid here. So first you need to understand, if it is said that it is valid, so what is Saint-Venant's principle, you need to understand. So let us check these demonstrative pictures. So first we will be seeing the pictures of where we don't apply any load initially. What is the initial condition of these pictures? I mean members. So initially a whole member, a solid member is taken, and then a member which has got an internal hole is taken, another member where an abrupt change in cross section is taken. So what if these members are subjected to a tensile load? So we will try to understand, and let us see initially how they changes, means how the tensile load is changing the material, or which is causing deformation, how the deformation is caused here. So if you see the first one, when it is subjected to point load, what do you mean by point load? A load which is applied at a particular point. So unlike the distributed load, suppose if you handle this particular length totally together and pull, okay, so this distribution, the deformation may not look like as it is appearing here, isn't it? So based on this loading, the stress concentration or the deformation is changing, and this effect according to Saint-Venant's is only till a certain length, so beyond which its effect is negligible. That's what Saint-Venant's theory explains, that principle explains. That is, the nature of the load, the effect of the nature of the load is only till a certain length, beyond which the analysis can be applicable, that is the stress can be considered uniformly distributed. So that is Saint-Venant's principle. And Saint-Venant's principle extension, if you it can be applied to other materials also, where you have got sudden changes in this, sudden changes or sudden discontinuities in the material. So discontinuities, the whole is a discontinuity here, abrupt change in the cross section is a discontinuity here. How the behavior of the deformation is there, we will see in these pictures. Okay, so as we know, here or here, where everywhere you could see there is change in the size of these lines, okay, whatever the lines drawn here, so which indicate the deformation there by strain. So we already know that strain is proportional to, that is directly proportional to stress. So obviously by observing these lines, we can attribute this same principle to stress distribution also. So here from these three elements, if you observe, so whatever the discontinuity is there, or wherever the load of application of point of application of load is there, or wherever there is abrupt change in cross section is there, so you could see there is more concentration of the stress. Okay, so this analysis will give you the idea that, so we need to take care of such discontinuities, and we need to, because it tend to augment the failure of the material. So that's why we need this analysis, and this analysis is based on the Saint Venant's principle. So this is considered to be valid in the analysis of strength of materials. Further, this is about the assumptions which are considered in the structural analysis of members. So that is the assumptions which upon which this analysis of or the study of strength of materials is based on. I hope these assumptions, this analysis of study of these assumptions is very useful to you. You understand your analysis will be based on these assumptions. I hope you will have better study of this strength of materials or mechanics of materials. So I hope you like this video. If you like this video, please like, share and comment. Thank you.